That's why it is called modified CAM-clay model. So it is applicable mainly to clays. It is an elastic plastic strain hardening model. What do we mean by strain hardening model? Note that I will be presenting another independent lecture discussing the plastic strain behavior, the strain hardening and the strain softening. I will be discussing them both in details. But for now, the plastic strain hardening model in soil mechanics describes how your soil will become more resistant to deformation after initially yielding. That the hardening means that it will be more resistant. Softening, it is less resistance. Initially, in general, soils deform elastically until they reach a certain yield point, as we know. When the soils reach the yield point, then we enter the plastic zone. That means the soil after unloading will never return to its initial shape. Beyond the yield point, they undergo the plastic deformations, and when the resistance deformation increases with further straining, they are said to exhibit strain hardening. So, as conclusion, the hardening rule defines how this resistance evolves with continued deformation, which can be very crucial for understanding the behavior in over-consolidated clays, and of course, it is essential in advanced soil analysis. The third important point that the modified CAM-clay model is based on the critical soil mechanics theory. What do we mean by the critical state soil mechanics theory? That means all stress paths end up on the critical state line. Let's go to this important figure. What happens in the critical state line? What do we mean by the critical state line? In this state, the most important issue is that there is no more change or volume in volume or stress. So it is, let's say, in physics, as we said, it is a steady state. We can call it a steady state. That means there's no change in the volume or stress. How do we establish this line, the critical state line? Mainly, we plot the void ratio in function of the ln p prime axis. So in this space, in this 2D space, we plot their variation, and then we will construct those lines. Let's first of all. Also, this line, it is plotted in a Q P prime space. What do we mean by Q? Q is the deviator stress, and it is calculated as, this is Q. It is sigma 1 minus sigma 3 in case of triaxial tests. P prime is the mean normal stress, and it is calculated as, it is 0.33 into sigma 1 plus 2 sigma 3, also for triaxial tests. And as we said before, E is the void ratio. What are those lines here? Let us discuss what are those lines. In this figure graph, we have the void ratio in function of P prime, which is, as I said before, the mean normal stress. This line NCL stands for the normal compression line, which describes the stress strain curve as a straight line in the E ln P prime set of axes. And this line is constructed using this formula. How can you calculate the void ratio as a function of the P prime stress? It is calculated as E equals to E0, which is the initial void ratio, minus lambda Do you remember what is lambda? It is the isotropic logarithmic compression index, as we said before. Ln p prime over p prime 0. P prime 0, it is the initial mean effective stress at equals to 0. So once you construct this, once you construct this curve, you can also construct Q versus P, and this is the straight line. Where do you remember M? This is M that we talked about, which is the friction constant. And as I said before, it is the slope of the critical state line, and this is the critical state line. So let's continue what is happening on the critical state line. The line in the E Ln p prime space, we are speaking about this curve, corresponds to the critical state. Links the critical void ratio EC to Ln p prime and is assumed to have the same slope as the NCL. This is clear that it seems those two lines, the critical state line and the normal compression line, it seems that they are approximately parallel. How do we calculate this critical void ratio? It is obtained first when we obtain this critical void ratio at the end of the loading when soil reaches the critical state. Let's remember, what do we mean by the critical state? There's no change in volume or stress. There's no increase or decrease in the stress, and it is calculated using this formula. So the critical void ratio EC equals to EC0 minus lambda Ln p prime over p prime 0. Finally, in the critical state, the part of the strain which is recovered upon the unloading, it is called, of course, the elastic component of the strain, and it is its symbol is EE. This unload deload line is a straight line in the E Ln p set of axes, and the equation of this straight line is EE equals to EYK Ln p prime over p prime y, where what is EY? The void ratio, which corresponds to the yield stress p prime y. K is the swelling index, which is defined previously in this lecture, and the critical state line plot is Q equals MP prime. M is the critical state parameter. Let's go again to this graph. Yes, this is a Q in function of P, and this is the straight line passing through the origin, and M is the slope of this straight line, and this is what we are speaking about in this equation. So this is an equation of a straight line passing through the origin with a slope called M, which is the critical state parameter. As I said before, M is calculated in function of the effective angle of friction phi prime. So here we discussed the elastic part, which is recovered upon unloading. What about the plastic part? The plastic potential is the same as the yield function because so the plastic potential is the same as the yield function because the modified chemical model uses an associated flow rule. Also, regarding the flow rule, I will be discussing it in details in an independent lecture, but for now, let us discuss in a brief what do I mean by associated flow rule, of what is the significance of the associated flow rule in soil models. It is based on the premise that the direction of plastic strain increment is normal to the yield surface. This rule implies that the plastic volumetric and shear strains are in the same direction as the increment of the stress ratio. So we have three parameters: the plastic volumetric strains, the shear strains, and the increment of the stress ratios. The associated flow rule means that those three parameters are in the same direction. So in general, in many soil models, mainly those that are based on the critical state soil mechanics as the modified Khan-Clay model, the associated flow rate, of course, is a covered assumption, as in our case. However, it's important to note that for some soils, the associated flow, the non-associated flow rules might provide a better representation. As I said before, I will be discussing later on in an independent lecture. What do I mean, or what do we mean by associated and non-associated flow rules? Concerning the yield function, it is an elliptical function, and it is calculated using this equation, which is function of QM and P prime. And the yield is reached, or the yield surface is calculated for F equals to 0. And those are the strain hardening for modified Khan-Clay model. Let us remember that the hardening rule is an isotropic hardening rule, as I said before, and it is obtained from increase in yield stress and from the recognition that the strain is made of two parts: the elastic part, which is related to swelling, and the plastic part, which is where we differentiate between the normal compression line and the swelling line. In summary, what is the critical state theory? First, there's three behaviors that should be explained. First, the elastic behavior, where the soil acts or behaves elastically, and all the deformations in this case are recoverable. The second is the plastic behavior. That means the stress state goes beyond the yield surface, and in this case, the soil will deform plastically. These deformations are permanent. That means they are not recoverable. And in this case, as the soil shears, the yield surface will expand. The hardening softening rule, let's remember that the modified Khan-Clay model follows a hardening rule. The size of the yield surface changes as the soil shears. If the soil is dilating, the yield surface gets smaller, and this is softening. This is not what will happen in modified Khan-Clay soils or models. However, if it's compressing, the yield surface expands, and this is what happens, or this is one of the assumptions of the modified Khan-Clay model. Also, in this slide, I'm summarizing again the three lines, which are the normal compression line, the critical state line, and the yield surface. So the information will be clear and well organized for you. This is the figure that shows the variation of the Q as a function of the strain. And look, in this case, it goes to the infinity. And here we reach the critical state. So thank you, and this is the first part of this lecture. In the second part, I will be discussing the applications and limitations of this model. If you are finding this information valuable, please follow us on YouTube, Facebook, and Instagram as the Geotechnical Engineering Library, and you can follow me on LinkedIn as Shada Sulaiman. Note that the lecture notes, the PDF slides, are attached in the description of this video below. Thank you.